Hey, so hello, Scott. I'm trying to do something.
How are you this morning?
I'm good. Kind of rested up. I slept all day yesterday, all day long.
Well, that's good. It's good to feel rested. Take it from somebody who can't get a good night's sleep for like a week straight, it seems like.
Yep. Let's see. Okay, that puts that there, and that puts us here. And yeah, okay. So we're talking about Rebekah again, and it's pretty much the same thing we talked about last time. And something I wanted to emphasize again. Now, when you listen to Rebekah, she's going to say it's just a story. And they just say they don't provide any evolution evidence. They just provide a story. Well, every paper starts out with a couple of things. There's let me see here. Yeah. So every paper starts out by saying, oh, there's a problem for evolution. This is a problem that we got to solve, right? So in the abstract, they'll frequently say, we don't know how this works, and we don't know how that works, and we don't know this, and we don't know that, right? And the creationists usually stop right there and say, see?
Yep.
They don't know.
Gotcha.
But then after the problem, they come up with something called a hypothesis. Now, Rebekah thinks the hypothesis is the evidence. She confuses those two things. Now, the hypothesis is our story or idea about where it came from. And a hypothesis has steps. And after we get the steps, we go deeper and we come up with steps within steps. And we keep trying to refine the story, the hypothesis.
It steps all the way down.
Steps all the way down. And then after we have the hypothesis, we look for evidence, okay? And she didn't look at any of the evidence in that paper, and we can go over some of that later on. And she just totally blew it off, and Nestle called her on it about 5 times while he was talking to her and said, you didn't look at the actual paper. He says, well, my readers wouldn't listen. Of course, they'd all get bored and they'd wander off. We actually looked at the evidence. And then she concludes that there is no evidence.
She's defending lack of integrity because it won't please her crowd.
Right. Because her crowd just wants a rhetoric. They have this problem, and then they come up with just a story, and there's no evidence for it. It's like bullshit. So now the distinction between a scientific hypothesis or model or story, whatever you want to call it, everything that we do when you figure out how crime happened or how something happened around your yard, your garbage is laying all over the yard, and you come up with a story about what happened. Some rabid raccoons got after it last night, whatever. You always come up with a model.
The theory of the crime.
Yeah. And then you start looking for evidence. You look around. And it's like you find these little raccoon prints in the mud, and it's like, oh, that is the evidence. And now that supports the hypothesis. Now, there's no reason why we should be so close-minded as to think that God didn't get hungry in the middle of the night and want a snack and open your garbage can miraculously, right? So, I mean, you got to be open-minded about this, right? So Rebekah says that because God could have done it, we should abandon the idea that nature did it. Is that what she's saying? You see what I mean?
I see what you mean.
The problem? I mean, if our garbage is strewed all over the yard, why are we being so close-minded about it to not think that was Jesus doing it? I don't understand.
Jesus might have been looking for something, and just, his back was still sore from that cross, and he just didn't want to bend over and pick it up.
Right. Yeah.
Think about what Jesus went through for you and pick up your own garbage.
Yeah. So we got a distinction between the model or hypothesis or story, whatever you want to call it, and the supporting evidence. And this is the distinction is crucial for understanding how the origin and the evolution of spliceosomal introns are discussed in the source material. And so here we have this thing where we state the problem, we create our model, we go out and find evidence. And that's exactly what the paper did. And I can show you what evidence they claim to have found. Now, all of that evidence can be just dispelled by saying God did it. But there we have a problem. And Nestle pointed out that problem, and Dr. Dan has pointed out that problem, that if you believe in last Thursdayism, you can believe that everything was created just so last Thursday. That's going to eliminate anything else, any other idea, right? It overrides it. Or we can imagine that we're a brain in a vat, and somebody's just feeding us this information, and it's not real at all. Some evil scientist from another dimension has us just my brain in a vat, and you don't exist, Scott.
Wow.
Yeah.
That would solve a whole lot of problems if I didn't exist.
It would. It would solve a whole bunch. Anyway, and then let's see. So now you wanted to go down and let's see. Okay. She comes up with alternative splicing.
Okay. She says it has intentionality, but what she does is she projects intentionality on it.
Right.
Look at that. It's going so fast and it's just hitting it so hard. It can't be through evolution. It can't have happened over a long period of time.
Right. So all that she claims to have provided all of this evidence against evolution by showing us her own papers, and what she's actually providing is complexity. She's showing that cells and life and biology is complex, and the more we learn, the more complex it seems, and that's because we are filling out more of these steps, right? More and more steps within steps within steps. And then she goes on and comes up with it's like, oh, it's so complex it can't possibly have happened. So anyway, you want to talk about this, which is all her evidences against evolution. And she added alternative splicing up here, which is her latest. Are there 16 of them? 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay. These are her 16 episodes.
Yes.
Yeah. Well, she said she has episode number 16. This is so she has 17 evidences. We're going to pluralize it. Oh, so we got a person listening to us.
A person I've not encountered before that I recall.
Oh, Laborious Cretin.
Welcome aboard, Laborious Cretin.
Thank you.
That's a cool name when you think about it. Laborious Cretin. It's almost like he's a Roman or something.
Right. But has Laborious Cretin hit the like and subscribe button yet? I don't know. Got to the Gaps themes, seeing important parts, chunks, and using things. We have to be
likable.
Yeah, I know. We'll try. You can profile their groupings and bias sets that come with bias blindness. Yeah, it's just blindness. It's like I don't know if you were on with the beginning when I was talking about a very simple example of garbage scattered all over your yard. And you go out there and you say, oh, I have an idea that raccoons probably got into my garbage last night. You go out and look for evidence and you find tracks, and that's evidence. But we are being closed-minded if we don't say that God could have done it. It could have been intelligently designed. That whole mess out there. I mean, obviously, to open a garbage can, very complicated, takes some intelligence, that sort of thing. So it could have been God. God could have done it. I don't know. Anyway,
or it could have been aliens. It could have been aliens coming from way back in time and messing with your garbage.
Right.
Thank you, Laborious Cretin.
Cool. Thank you. So let's see. Okay. So now we're going to back up a little bit. We want to get back into talking about main point when listening to Rebekah is she's going to talk about a story, and she's going to talk about evidences and she is never going to look at the evidence, and she doesn't understand the difference between a hypothesis and evidence, and that's a problem. She thinks of the story, the hypothesis is the evidence, and that's not how it works, and I wish she would get that straight in her mind. So here are her evidences against evolution, and what they amount to is alternative splicing is really complicated. Ribosomes are complicated. Circulatory systems are complicated. Gene origination. You want to comment on a few of these, Scott? DNA code, complicated. Complicated.
Yeah, I'm assuming that she's using complication or maybe lack of fossil evidence for some of these, but and yeah, nuclear pore complexes, Sal. She's mimicking Sal in a lot of these.
She had Sal on for that one. She actually had him on. It's complicating. I'll put complicated. Okay, so it's just complicated. That's it. That's what all these amount to, right? Oh, no, she's got, okay, a little bit more. She's got diseases caused by mutations, okay? And she's got some fossil stuff, too. So let's see. Okay, nuclear pore complicated, collagen complicated. Oh, no, collagen and blood vessels in dinosaur fossils. So that would be different than complicated. So now on the right side, we've got like a little bit of a difference here. Okay, so no, we didn't find blood vessels in dinosaurs. We found imprints of blood vessels when we started magnifying those fossils at higher with better instruments, and we found that fossils are really cool. They record a lot of information, and we found traces of collagen. We did not find collagen in blood vessels. We found the traces of basically the fossils of molecules. They were modified amino acids, and they were in the right sequence, so we could identify collagen. And in fact, they retained some of the properties, and collagen is one of the most preservable proteins that we know about. It's very, very strong. It's why our bones, muscles, most of us is held together with collagen. Because it's a very, very strong and well-preserved molecule.
May I comment on the next to the last item real quick?
Oh, sure.
1,000 bat fossils, but no bat predecessor.
Yeah, what the hell?
I went to Copilot because, usually I encounter these arguments without any prep time. So I basically asked Copilot, just as a quick reference, list 3 or 4 fossils with links to images that are predecessors to bats. And I got 3 or 4 predecessors.
Okay.
Protictus, Paleocene, 60 million years ago. Not a bat, but a possible ancestral mammal with traits that may have led towards bat evolution. Small insectivorous with arboreal adaptations. And so when you view the image, it's showing.
What?
It doesn't like that image.
Oh.
So before that, let's see. Paleochiropteryx tupiodon, 48 million years ago, found in Germany, had short wings and long tail, likely adapted for maneuverable flight in dense vegetation. Onychonceteris finnii, 52 million years, considered a basal bat. Now that's important. It's a basal bat, possibly capable of flying, but lacked full echolocation. So they don't even know if it could fly, and it didn't have echolocation, and they can tell that by, the structure of its bones and everything. Primitive limb proportions. So to say that there is no bat predecessors is to say I didn't do my homework, or I just did the homework and
ignored it.
Yeah, and rejecting what an entire field of specialists consider basal or predecessors is not the same as having studied and come to a reasonable conclusion that something isn't true.
So which ones did you mention? Let's see. Onek. Oh my God, that's a bit. Onychoncytrus.
I didn't say classification was easy.
Onychonycterus, that's what it is. Tenae, from the same formation, which is considered more primitive. It has claws on all 5 digits of its wings, for example. So they have bats with claws on the wings, and then let's see what else. Even older pieces, fossil bat teeth and jaws from 55 million years ago. Let's see what else we got here. We don't have fossils of the protobat, non-flying or partially flying mammal that gradually evolves into a full bat. Timing, location, and pathway of the origin of flight and echolocation in bats remains unresolved. For example, we just haven't found them yet. So I don't know. But we have found simpler or different organisms that are not bats, particularly. Anyway.
Now, if you back up on this list, thousands of dinosaur fossils, no predecessors. I don't know if we did this on our last video, but I know we talked about it.
We mentioned it, yeah.
Just a quick Google search will find you several examples of fossils of archosaurs that are transitional between archosaur and dinosaur traits. So what are you talking about, Rebekah?
Yeah, she's just highly wrong about that. It's just like, okay, for one thing, the word dinosaur is a little iffy to begin with, and we have just a whole huge line of fossils from fish to dinosaurs, basically. I mean, it's just filled in like crazy, thousands. So I don't know what the hell she's talking about. Millions of fish fossils and no predecessors to fish. That is just such bullshit. So she basically fish, or what we call fish, which is also not a biological term. It's kind of a common man term, right? What we call fish, we have all kinds of really early jawless fish and different fin structures, and let's see, the Sarcopterygians and the other one, and the fin fish and lobe fin fish, basically, or the ray fin fish and lobe fin fish, and we have that whole thing, right? And then going back before that, what she's talking about is the origin of vertebrates, which we have just all kinds of information about with notochords, real primitive spines developing, and it goes all the way back right to the Cambrian. So she's lying about that too, or she doesn't understand it, or she just rejects it as soon as she sees it. But there's a whole bunch of stuff about the evolution of early vertebrates and how vertebrates developed, and then eventually end up with something we would call dinosaurs. And it's just nonsense. So I don't know what the hell she's
now. Getting back to the fish, I just pasted, or actually I had to type it since that's an image, that statement about fish and fish predecessors. Yeah. And once again, no, that statement is incorrect. I mean, even people-pleasing AIs just can't find a good way to complement that question. Paleontologists have discovered multiple transitional fossils that document the evolutionary steps, and those include Ichthyus, which Ichthyus is fish. One of the earliest known vertebrates, had a notochord, gill structures, and paired eyes, but no jaws or bones. Considered a basal craniate, close to common ancestor of all vertebrates. So you would have to be a vertebrate to be a fish. So there we go. Mylocunnimingia, 518 million years ago. Evidence of muscle blocks, myomeres, and a head with sensory structures, but lacked a vertebral column, but had features placing it near the base of the vertebrate evolution. Paired eyes, gill bars, and notochord. and early vertebral elements. That was Metaspringnia. So you don't have to look very hard to find these examples. And these are from fossils. So what in the hell is she talking about?
It would be interesting to hear her explain what the hell she's talking about. And I don't know if it would be possible to have that conversation with her, but maybe if I ever get on one of her streams, she has them late at night, and she never she does them like we do, like an hour before. So you never know when she's going to do it. But I would like to ask her about the fish, particularly millions of fish fossils, no predecessors, because predecessors to fish, I mean, they're everywhere. This is something that is really well studied. Anyway, you mean like goldfish?
Yeah. And
what do you think?
of course, coevolution enzymes, I'm back on the left-hand page towards the bottom. You know, that's just not an argument against anything. All you're saying is it's hard, and it can't happen in real time if it's hard. You need a God, and that's just not an argument. That's an argument from incredulity or something like that.
Yeah, it really irritates them when I say this. And they always say, oh, don't just tell me that that's how evolution works. But the co-evolution of enzyme is exactly how evolution works. If just a enzyme out in the middle of nowhere that did something all of a sudden popped up, and there was no other enzymes that worked with it or earlier enzymes or pieces of that enzyme, then we would have a problem. But the co-evolution of a whole lot of biochemical pathways is how evolution works. And I got something on that a little later, I think. But anyway, so it's not a problem. But yeah, everything, all 8, I think 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I think on the first page are all, oh, it's complicated. It couldn't have possibly happened. And nuclear pore complexes cell. He is just ignorant about this nuclear pore complex thing. There are signals that we have found in single-celled animals that have no nucleus that are very similar to these nuclear pore complex signals that he is so excited about. And so we have genomic fossils of all of those things. So anyway. So now what she's talking about, let's see, in this video, which we haven't even begun to show yet, have we? Did we show anything? Should we do a little bit of video to kind of get an idea?
Give us an idea.
Idea. Let's see. Okay. Well, come on. Why won't it work? Okay, I gotta go back to this. StreamYard has some issues, I think. Let's see. What does she got? Oh, we'll try it right here.
I think Dr. Dan is wanting to go back to like just broadcasting through OBS because of the issues with StreamYard.
Really? I thought about broadcast. I'd never cracked into that, but it would be nice if you could do that.
Machines that mix and match those genes depending on what is needed. So whatever type of protein is needed, they take from what's already there and they mix and match them to make the gene the way that needs to be for the specific protein machine that's needed. Now, why is this a problem for evolution? Well, it's obvious to me, and it surprises me.
Oh, it's obvious.
Yeah. Let's see. So,
vibes.
Okay.
This is science by vibes.
Yep, it is. So it's just really cool to listen to this, and I want to listen to it one more time a little earlier. Let's see.
What happens is that you have an army, hundreds of protein machines that mix and match those genes depending on what is needed. So whatever type of protein is needed, they take from what's already there.
Whatever type is needed. Okay, that's That's the frame of her mind. And that is a designed frame of mind. Yeah, chemistry. Let's see.
Maybe in the presence of those other complexes, a protein is constructed that happens to be what is needed for a particular function that we have in mind. I mean, the DNA doesn't care; it just makes its things, and it will make that thing, 15% of the time. And here you have all these machines making proteins, and 15 times out of 100, they're going to line up and match. It's a stochastic thing and not just a mechanistic thing that requires anticipation and planning.
Right. 1-2 switcheroo. Alternative splicing is not a feature of how well spliceosomes work. Now, what she does, she talks about, she just discovered alternate splicing. She had never heard of it before, apparently. And she was like, oh my God. So you mean the same gene produces more than one protein? And that is really common. It's like 90% of the genes have some sort of alternative splicing going on. And she's like, oh my God, that shows, how complicated it is and how no. Okay. And then she goes on to talk about the evolution of spliceosomes and how remarkable the spliceosome machine is, right? Well, the problem with that is alternative splicing is not a feature of how well it works, but how well it breaks and how it fails over and over again and creates different splices rather than always the same splice, right? And when it creates these multiple kinds of, or basically multiple flavors of one protein, some of them happen to fit into the machinery in such a way that it's beneficial to the organism. If there are a lot of them, some of them are going to lock in and they're going to do something. And when it's beneficial over time, that beneficial protein will end up becoming relied upon. So if the spliceosome worked perfectly every time, we'd only end up with one protein per gene. It doesn't, so we end up with a mess of proteins. Like you'll find a handful of proteins that are just pseudogenes that end up being produced and they don't do anything. They don't lock into anything and they don't do anything. And then every now and then they will lock into the machinery. So she's kind of misrepresenting what this alternative splicing means. And she's equivocating on two different topics. One is the evolution of the spliceosome machine, and the other one is alternative splicing. And somehow she sees these two things as the same thing. So she thinks that the machine got better and better and so good at it that it decided to start creating alternate splice proteins just as they were needed. And that's totally backwards, not how it happened. The machine was not perfect. It produced a lot of different versions of proteins. These different versions of proteins are eventually going to hook up and lock in and create some pathway. And some of those pathways, rare, but it's going to happen, are going to be functional. And we rely on it. Did I make sense, Scott?
That makes sense. And we have plenty of help in the side chat. What's
going on?
Laborious Cretan, Deconverted Man, and Nitty has joined us as well.
So we should pay attention to the side chat. Anyway, what is alternative splicing? Okay, I showed you in an earlier video. Basically, we got a long gene up here at the top, right? You see this gene. And this gene has these exons, like exon 1, exon 2, exon 3, 4, and 5. And this is a vast misrepresentation, because if we were to show these exons the size that they really were, these are introns, the part that gets snipped out right here. If we showed them the size that they were, they'd be way, way off the page, about, maybe 3 feet over, right? The introns are a lot longer than that. So the part that gets snipped out. So understand that this is a little bit of a misrepresentation. You remember when I showed you that I showed you an actual gene on the genome browsers, and those exons look like little tiny vertical lines
Mhm.
because they were so tiny. Well, they expanded them here for purposes of explanation. So anyway, this is a misrepresentation. You should know that. The intron, I consider junk DNA for the most part, and it is really huge. These things are really long. They're not short. Okay, so the exons come out. It gets transferred into RNA, and we have, the junk, and we have the good part, And then what happens is oftentimes the first exon there's a number of different ways for alternative splicing to happen. That's the other thing. If this was designed, and if the spliceosome was this wonderful machine that created alternative proteins, it would always use the same method all the time. There are a whole bunch of ways that we can end up with alternative splicing. I think there are about 6 of them. So what happens is sometimes one of these exons will get skipped and we'll end up with a shorter protein, like right here. Or let's see, what is this one? This one, I forget what this one does. It's hard to tell. Not sure. But anyway, so we end up with 3 different proteins with the same gene because of differences in how they splice. And one of the reasons for that is in the middle here. And do I have that? I don't have a picture of that. I'm sorry. I should have a picture of that. She has one. But anyway, one of the reasons is these introns, knowing where an intron is, relies on this, what is it, a GTAG, a GT. There's usually a GT right here, guanine, thymine. And there is a AG on the end, okay? And in the middle, there's kind of a consensus sequence that allows this thing to get snipped out and it pivots and it forms like a lariat. And then it joins these 2 ends together on the other sides of the GTAG. And oftentimes this piece right here, this consensus sequence, is not perfect. And sometimes it gets missed by the spliceosome. So it'll basically not snip it out, or it will miss the consensus sequence on exon 2, and it'll skip that exon. So there's a lot of reasons, and the reasons are that these things are not perfect. It's not a perfect machine. It doesn't work like a watch where you have gears that fit together. It works very stochastically, and we end up with different combinations. So it attests to the fact that the spliceosome is not perfect, that we have alternative splicing. And Rebekah misses that. She sees it as God being this clever designer that he used all these like different weird, like sometimes it works and sometimes it doesn't. What the hell kind of a design is that? 60% of the time we'll end up with protein A, 20% will get protein B, and 20% protein C. Maybe. So it just doesn't make any sense to think that
roll the
that's
dice.
design. Yeah, roll the dice, basically. Okay. So these are the different types of exon skipping, are called cassette errors or cassette exons. It's the most common form. So it will miss that AG right before the beginning of the next exon. Somehow something won't work right, and it'll skip that exon. Alternative 5, let's see, use of different donor sites at the 5'. Okay, let's see. So we end up with, occasionally we'll end up with one more exon on the left side that ends up being transcribed, and I think that's alternative 5' splice site.
Okay, now it's called, you're calling it 5'. Whenever I've seen that listed, I've just called it 5 foot, thinking, well, I'll bet if you stretched it out in real space and everything, it would be 5 foot long, and that's why they call it that. So you're telling me no, it means prime for some reason.
Yeah, it has to do with the nucleotide, and we call this by convention the 5' end of the DNA or gene, and we call this the 3' end.
Gotcha.
So just to differentiate it, just to keep our stuff straight.
It's a label.
Yep. So there's alternative 3 split. Let's see, 3' would be on the end, changing the end of the exon, use of acceptor sites at the 3' end. I'd have to study some of this shit more to give you a good idea what's going on. Mutually exclusive, 2 exons are never included together. One or the other is chosen. That's interesting. That would be an interesting little screw up of the spliceosome, where it would get one, or maybe it'll miss that one and it'll get the next one, but it won't get both. Intron retention, that means that the intron never got spliced out. It ended up getting translated into the protein. That is kind of rare. Alternative first exon is really common, I think, where it will, the transcription of the gene doesn't start until it skips that first exon, goes on to the second one, gets a better signal, and starts transcribing there. So that happens. And then last exon, which is really rare, where it will end up with this signal that, oh, we're going to stop transcribing the gene. It's called a polyadenylation signal. And every now and then, it's a bunch of adenosines or A's, GTCA. It's a bunch of A's together. It's a certain signal, and it tells it that, oh, the gene is ending here. We got to quit transcribing. Every now and then you'll end up with a weaker polyadenylation signal, and that will get hit, and it will not transcribe that last exon. So, okay. Now, what else we got?
Very okay. Dave just joined us. Hey, Dave.
Hi, Dave. Hi, Dave. Yeah, so I looked at the commonality of this stuff. So we found that like 90% of these genes actually have alternative splicing. And see, and it shows the different kinds here. How often it is, 35 to 40% is exon skipping. Then let's see, intron retention, 5 to 10%. Smaller than 5 is mutually exclusive exons. So that's sort of an odd one. And these are just, they're basically, they're mutations. These are mutants, okay? Different ways to splice that protein. And I can show you, let's see here. Where are we? Turn that on.
It can't be mutants because mutations lead to disease and death.
Oh, diseases, right. Yeah, they never work. Okay. So, like a protein, this big glob of protein, right? Which is folded up in all these different ways. What it'll have is some part of this protein will have an active site, basically. Like this one right here might get pinched together with maybe a zinc ion. We'll kind of pop that together right there. Or maybe 2 cysteine proteins will bond together, basically SS. They get rid of the H and they bond together. But anyway, they'll pinch it together and it ends up having an active site, right? And there are there can be more than one active site. Like this thing up here might hook onto ATP, which is the energy thing in the molecule, and it might twist this molecule in a certain way. And this part down here will actually do some enzymatic reaction. And this part here will attach to some other protein. So basically we end up with like a complex or whatever. So there's all these different ways that these different domains, and let me draw domains. So there's something called domains in proteins, and we can find these different areas in the protein that do different things, right? So these domains are kind of like, if you imagine, if you have a machine shop and you have a machine that with a clamp that will hold your work, basically, okay? The clamp that holds your work is one domain. And then you have this little adapter where you can put a certain cutting tool in it. Or you could put this cutting tool or that cutting tool or another cutting tool, right? So you can swap out these different cutting tools. So you can swap out these different domains, basically, and they'll do something different in this active.
Or like one of those screwdrivers that can take a million different heads.
Right. Yeah.
Slap them on there and hope they hold up.
Yeah. Yeah, and as it turns out, these domains kind of fold into their own little kinds of machines. And what happens is sometimes proteins will get chopped in half, and we'll end up with one little machine here and one little machine here. Other times they'll get joined together, so there's two of them, and we'll end up, and these will mutate into some other different kind of thing, and we'll end up with a different protein. And so any cell is going to have this massive mix of thousands of different proteins floating around, from the nucleus. So they have this mess of proteins. And what happens is, if a cell is viable, enough of the right kind of proteins will be present in the cell so that the thing can survive. But every now and then you'll end up with a little mutant that does something that ends up kind of working and lending a little bit and making that cell a little bit more efficient. And it's just this absolute mess of different kinds of things floating around in the cell, moving around at what would look like to us about 1,000 miles an hour, bouncing off each other and flicking around and whatever. And this whole machine ends up either working or not working, and that's where natural selection comes in. So if one of these things one of these little mutants ends up producing too many copies of itself and it kills the cell, then that cell ain't going to make it into the future, okay? If one of these little proteins copies itself and it ends up doing something viable, then that's going to make it into the future. And so you got to imagine this absolute mess of wannabe proteins floating around, and occasionally a few of them will hook up and they'll survive. If they don't, the cell will die and not make it into the future. So we're only interested in the ones that actually hook up and either do nothing, they do no harm, or they do some good. That's all we end up with natural selection. So that's how it happens. Oh, cuss we apes, that why? Why do humans have hair? Oh, do we have hair? I don't. Speak for yourself. Let's see. I'm bare-chested and bare-headed. So anyway. Okay, so what else? We're at 45 minutes. Scott? Where's Scott? I lost Scott.
We're about 3 minutes away.
Yeah, okay. We talked about 45 minutes. Okay, let's see. So review. So first of all, her equivocation between alternative splicing and the evolution of the spliceosome. And the evolution of the spliceosome, we can save that for another episode, right? We'll look at that paper and we'll talk about the evidence for evolution of the spliceosome. But anyway, she equivocates alternative splicing, which is a spliceosome not working so good, basically.
Yeah.
And actually, that ended up being a feature of the spliceosome not working so good. It ended up giving us these alternative blood proteins with mix and match domains.
It's
and
like,
the other
using duct tape to repair your fender after an accident and realizing, hey, it's still up there. I don't need to take it in to get fixed.
Yeah. And the most important thing is this, with her constantly going on about stories, and she misunderstands the three parts of the paper, which are stating the problem, giving us a story, model, or hypothesis, and then finding evidence for that hypothesis. And in the spliceosome, in another episode, we can show you what the evidence found was. And then the third thing is that she can just say the evidence is just the way God did it. And we can say, but Rebekah, you're not talking about science anymore at all. You're talking about last Thursdayism. You're talking about metaphysics. You're talking about anything can happen. And if anything can happen, we can't know anything, right? If we find the garbage, go ahead.
Can I repeat my critique of her use of the term story again? I don't want to beat it to death, but maybe we have a
no, we do. We want to beat this thing, this son of a bitch, to death. Go ahead.
Rebekah is engaging in basically what is known as a Tukokay fallacy, you guys are doing the same thing. And our
Right.
critique is, well, your creationism is just another myth. It's just another
Story.
another set of stories from a storybook, and it is. I mean, you're trying to make it fit a myth, Genesis 1 and 2, the Great Flood in some cases, and those are literal stories that people told around campfires or at a temple or tabernacle. Oh, sorry about that. Can you hear a bell going ding ding?
That wasn't bad. It wasn't
Okay.
intrusive.
That just said 45 minutes is up, and that's what those are. Basically, the Genesis creation accounts are some reformulation of earlier Mesopotamian and Canaanite creation accounts that have been, dummied down or retold in terms of a particular group's favored myth. And the gospel stories, borrowing Hellenistic elements. A lot of scholars are pointing out some Greek storytelling, Hellenistic storytelling that is very similar to the Gospels. And that's what those are. They are stories. Now, what happens in science is you form the hypothesis, you gather data, you do statistical analysis on it, you confirm things, but then you have to explain it to people in a way that they can understand. So you engage in narrative, an explanatory narrative, and it's falsifiable. In other words, if I say that this particular gene merged with this gene, and that's why we look a little bit different from the chimpanzees or whatever, you can take that and falsify it. You can't falsify a myth. You can't falsify a real story. It's just a story. But what you can admit that you need to change your explanatory narrative based on changes in the data that are, give us a more accurate picture of what really took place in the past. So she's committing an equivocation fallacy, and she's saying, but you scientists, you science-based people, you evolutionary thinkers, you do the same thing as we do. And it's not true.
Yeah, good. Yeah, and the other problem with it is, like our hypothesis, our story is basically that X caused Y, right? And then that caused Z. So what we're doing is we're creating this hypothesis about this path of things. And if we find out that X could not cause Y, or if we found out that Y is impossible, then we would falsify our hypothesis. But if we look at this, X caused Y caused Z, and we find some remnants in the genome of Y and X, basically, in simpler organisms. If we look at Z and we find remnants back in Y and X, okay, that becomes evidence for our hypothesis. And if we find something today in the lab where X can cause Y, like some mutation, the way it works, then that becomes evidence for our hypothesis. And at any point, we can prove it's impossible. Now, but what she is saying is that X caused Z, right? That God caused Z. First of all, X has to be possible. You have to show me evidence that X actually exists. And if you can't show me, and this shifts the burden of proof back to Rebekah, you have to tell me why I should believe in God if I'm going to start doing God-based science. If I'm going to think about intelligent design, you're going to have to convince me that there is some kind of a thing, like a man who can make watches that lives in another dimension that is so powerful that he can design things with little tiny fingers like molecules, and that X can create Z. You're going to have to fucking prove X. Otherwise, me, the lifelong atheist, has no reason to believe you. And I welcome her to come up with any evidence that she has. So anyway, okay, now we're at 45 minutes. We got people. That's cool. We have people actually listening to us.
Our longtime friend James Apperson showed up.
App persona non grata. Yep. and laborious cretin. Let's see here. What do we got here?
Birded Man and Nitty did a lot of commenting back and forth as well.
Yeah, he did. Recurring theme, always missing important parts, chunks, and trying to play the god of the gaps. The current programming for them is pushing quantum quackery, right? Yeah, quantum thought, and that's a big thorn in my side, this quantum bullshit and brains and dualism and all of that. A whole other thing.
Look,
I
know it's going to extend our time here a little, but
yeah.
We also have to point out, I think, that one of the flaws in Rebekah's approach and her thinking is that she thinks that any one particular aspect of the theory of evolution, or theories of evolution actually, can be disproven or discounted, then that makes the whole thing tumble down. When in fact, you know how in a building that you have different beams that you really can't move or take down or do anything to because they're support beams for the whole building.
Yeah.
The spliceosome is not one of those support beams.
No.
There are others that are, that if you falsify them, the building may come crumbling down.
Yeah.
But spliceosome, some particular aspect of cellular activity, the existence of some chemical going on that we may or may not have a hard time accounting for in evolutionary theory is not going to bring the whole building down. And
right.
And so maybe we need to do another 45-minute session on what those particular pillars are. But
yeah, I would like to, what would falsify evolution? It's really difficult because this stochastic craziness that's going on in the cell, the complexity is great enough that it's very difficult to find something that doesn't have a pathway, right? Like you have to find two parts, like in this diagram here, you would have to find that, that this pathway was not possible. So you'd have to find some pathway that was impossible. And that's difficult. And I know that frustrates them, because what happens when we find some new thing out, oh God, we were wrong about this. We always have a story or a hypothesis to get around it. We'll always find another pathway. So I understand their frustration, but that is exactly why life exists today, because there are so goddamn many ways to get from A to B or from X to Z.
Yeah, anymore saying that evolutionary theory is disproven is like saying, oh, there is no biology. Yeah. Biology just doesn't happen.
And the other thing they do is they try to, they'll say, oh, well, these two steps, if you multiply them together, we got, this probability times this probability, whatever, and you'll end up with a whole bunch of zeros. Okay. The problem is that we don't know these probabilities. You don't know those probabilities, so you can't give them a value. You can't just say, like Douglas Axe did, 1 in 10 to the 77, because you're ignoring the 1 to 10 to the 70th that are, or 50th that are possible. Okay, you don't know the probabilities of these things because you don't know exactly what the steps were. You don't know how many organisms were out there, how long they were out there. So you can't say something is improbable, basically. So they can't use probability. They're fucking back of the envelope probability calculations. We can just tell them, stick those up your butt, because those don't work, basically. Anyway, are we done? Scott?
I believe I am done. I believe I have said what I need to say to help stand up and oppose the tide of misinformation and pseudoscience that has been promulgating through our culture.
Yep. And before we go, you mentioned somebody that interviewed Bernardo Kastrup,
Alex O'Connor.
Alex O'Connor interviewed him. So
yeah, I put the link way up there in the side chat. Here we go.
You didn't? Did you put it in private?
I put it in private chat as well. But yeah, Bernardo Kastrup is kind of an odd asserter of idealism, and claims, I guess, scientifically and whatever ism that you want to use, to have just this great, wonderful argument against materialists and physicalists about idealism, that that basically everything is like this one substance, and that we're all made up of it. It's all consciousness.
Yeah, we're made of consciousness.
And just like humans can have multiple personalities, everything is just basically a split off of the great consciousness of the universe. And that we're an expression of some sort. We're an altar, I guess, to the consciousness.
Yeah, an altar, is that what he calls it?
Well, that's what people who actually have multiple personality disorder, and I don't even know if that community of people even want to call it a disorder anymore. They just have multiple personalities. That's what they kind of call themselves. They're one of the personalities within their person. Is they call them, I think, altars. I could be wrong. So
yeah, you're right. That's where you got it from, right?
Yeah.
Yeah, and I linked that in my description too, in case you want to find it later. So, in case you don't want to look at chat. Oh, one other comment. Why did Rebekah turn off her live chat on her video? Does she always do that? She turned it off on this video. She must not have liked what somebody came up with or something. I don't know.
All those pesky people using facts and science to refute her.
Yeah.
I don't want to. I'm not going to take the time to put the link in there, but go back to the most recent Dr. Or Creation Myths. Is Dr. Dan did a kind of a replay of his conversation with Rebekah, where she just kind of dived out of the conversation because he said something about her thinking being wrong or something like that. He said, well, if you're going to say that about me, I guess we just don't need to talk. Goodbye. You know.
Yeah, she hung up. Yeah, she kicked him out. Yeah, that was pretty cool. Dan got his butt kicked out of Rebekah's stream. Anyway. Okay. The cosmic psychopath has multiple personalities. Got self in the eye. Cool. Okay, we're going to end. We don't want long streams, so goodbye, Cruel World.
Thank you for joining us, everybody. Like and subscribe, please.
Thank you. Thank you. Goodbye, Cruel World. Are you ready?
I'm ready.
Bye.